transformers. So we worked through the full definition of the transformer last time. We have a sequence of words. So we have a sequence of layers up to layer K. Each layer looks the same as every previous layer, except they have different weights, so different numbers in the weight matrices. And then finally, we get an output. We'll call these outputs the Z's. And there are different tasks that we can solve here. We can consider just autoregressive language model, that is predicting the next word. So we have our target here. Target meaning like this is the sequence that we want to predict. Our target sequence is what? It's the original sequence that we input into the model, except shifted to the left by 1. That is, given W1, we want to predict W2. Given W1 and W2, we want to predict W3. So we want to predict every word from all the words that came before. So our target sequence is W2 up through Wn, and then we'll also say we want to predict EOS, end of sequence. So EOS means end of sequence. This is what we also want to predict. And we're going to be defining probability distribution. Probability of a particular word. Let's say probability of word I plus 1 given. Sorry, I made one small error here. The target sequence are not actually the vectors. They're not the word vectors. They're the words themselves. It's a small distinction, but like what we're trying to predict is just what the actual next word was. Like this was the word banana. We want to predict the word banana. Okay. So we want to find the probability of word I plus 1 given word 1 up to word I. How do we do that? So we're given words 1 through I. We want to predict the next word. How do we predict the next word given what we've done in the transformer and the outputs in the transformer? What do we do? So the transformer takes in a sequence of words. It outputs new representations for each word, Z1 through Zn. We want to use these representations in order to predict what the next word is going to be. So what do I do? Multiply those representations by the output matrix, and then get the softmax of that, and then give the words a resampling, and just say high probability. Well, you're trying to calculate what's the probability. You know, so when you're talking about generations, that's great. But I want to know for the correct next word, how do I compute this probability? And you gave me most of the ingredients. Okay, so you're right that I'm going to take the z's, run them through output embedding matrix to transform them into a new vector that has number of dimensions equal to the size of the vocabulary. So I have 1 score per element of my word in my vocabulary. I'm then going to do a softmax that gives me a probability distribution over words. Perfect. But I want to compute what's the probability of the word that occurs in position I plus 1. So how do I do that? There's one important missing ingredient in what you said, which is which z do I look at there? I'm not going to look at all the z's. I'm predicting this particular next word. So what does llama love? Or who does llama love? So I'm going to have z's associated with this, right? So I have this is z1, z2. Which z do I use to predict what word comes after loves? 3? 3, really? Only z2. Only z2. Z2 is going to contain information about the entire previous sequence. Why is that? It's because of attention. So because we did attention, Z2 contains information about both loves and llama. So we're going to use Z2 to predict the next word. So in general, if you give me words 1 through I, and you ask me to predict the next word, which Z do I look at? Zi, great. Okay, so this is going to equal softmax of what? Of an embedding matrix, an output embedding matrix, so I'll call it EO, my output embedding matrix, times Zi, the output representation for the ith word. So that gives me back a probability distribution, and now I want to find the actual probability of this specific word. Like this was mama here, and so I now need to look up where did mama occur in this distribution. So I'll call that, I'll use this notation here, where what I mean is, this is like a list of numbers, and I'm just looking up what's the probability of this specific word in this list of numbers. Questions about this? Okay. So what was it? Yeah, go ahead. Yeah. Exactly, because what we're inputting into the transformer, okay, you got to exactly the question I was going to ask right now. So what the transformer actually sees is this. It sees this full sequence. Llama loves mama. And is that how you spell mama? Probably not. It doesn't look right. Let's pretend it's right. I don't know. I'm sure someone spelled it that way. So So we have the transformer sees each of these three words and it sees them at the same time, right? So what we get out from this, if we input a three-word sequence, we actually get out three different next word prediction problems. We get out a problem that corresponds to predicting what comes after llama. We're going to use Z1 to predict what comes after llama. We get a problem of what comes after loves. We're going to use Z2 to predict what comes after loves. And we get out the problem of what comes after mama, which is end of sequence. We use Z3 to predict end of sequence. So we get out three separate problems. Now, the issue that we encountered at the very end of last class is that as we've defined attention for Z2 or for word 2 looks at word 1 and word 3. So if we want to predict what word 3 is, that would be like pretty easy. We can just literally copy over, hey, like word 3 with mama. That's what Z2 will represent. Like, it already saw the correct answer. That's not what we want the model to learn. We want the model to learn actually how to do prediction. So if someone gives you a partial sequence, you can predict what comes after it. That's how GPT works, right? You give GPT a question, it predicts what comes after that question. A good answer. So we're going to need to adjust what happens inside our attention layer. So let's talk about that. And so what we'll be talking about is called causal masking for attention. Another way of saying this is preventing the future from influencing the past. We do not want the word mama to directly influence our representation for the word love. Now, there's only one time travel movie that actually makes sense. Does anyone know what it is? Yeah. Which one was that? Which one was that? Who's in it? I think I saw it. I think it was terrible. So no, none of it makes sense. Okay, because they all have the grandfather paradox, right? Which is go back in time, kill your grandfather, and how is that even possible? Doesn't make any sense. So there's only one time travel movie that actually makes sense. Tenet. It is not very loved, is my sense. I think it does not have a great reputation. Have people seen it? Yeah, you have seen it. Wow, that's surprising. I think this is the best sci-fi movie ever made. I mean, not least because it deals with time travel in a coherent way where that seems to be almost impossible. But it's also, I think it's fantastic. This is a controversial decision. Your grade will be improved if you share my opinion about this. I'm joking. Okay. Now, time travel does not make sense. Okay, that's the lesson here. It's very, very hard to get to make sense. In the context of language modeling, it makes no sense whatsoever. So we want to prevent it. Let's look at attention. So what does our attention matrix look like? So we have, let's say we have three words. We have this sequence here. Now, where attention, I'm not going to go through the full QKV computation here, the full dot product stuff we talked about. What attention gives you out ultimately is a probability distribution for every word. What it tells you is where does llama attend to? Which words? And it gives you a probability distribution over it. Which words does loves attend to? Which words does mama attend to? So we'll write it in this way. This is A11 is the probability that llama, the first word, assigns to llama, the first word. A12 is the probability that llama, the first word, assigns to loves, the second. So we're going to write down three different attention distributions. Why are there three distributions? One distribution for each row. Let's remember our sort of attention update formula. So this is how we compute new word representations from our old word representations. What do we do? Well, we have, let me give a simplified version of it, which is, so we have, let's say GI. So this is the new word representation for the ith word. This is equal to a weighted sum over, so j equals 1 up to 3. Why am I summing up to 3? Because in this case we have three words. Okay, so this is our new word representation here. And here is our old representation. So we have three different old word representations, one word representation for word in a sentence. We're taking a weighted sum over those old word representations. That's going to give us our new word representation. There are some details here I'm ignoring in particular. These are actually value vectors, right? Remember the value matrix and value transformation that we did. If you go back in your notes, you'll see me talk about value before. It doesn't really change anything here. The point is we have a vector representation for each word. Our new word representations are a weighted sum of those things. Why is this a problem? Because now llama, the word llama here, is trying to predict the word loves, correct? The attention that the word llama assigns to the word loves will be in general non-zero. So that means the word, part of the new representation for the word llama will include information about the word loves. And so the way that the model will end up solving the prediction problem, what word comes next, is it will just copy the information over from the word loves into the word llama. And that's a trivial way to solve the problem. It's not how, it involves no thinking. It doesn't actually allow you to do real prediction in the real world, like where you don't know what the correct answer is. So is the problem clear? Are there any questions about it? We have leakage of information from the future into the past. We need to prevent that leakage. How can we prevent that leakage? We don't want current word representations being influenced by future word representations. So what do we do? Yeah. Perfect. So we're going to not use, for the word llama, we're not going to use any of the word representations for loves or mama. For loves, we will not use the word representation for mama. We'll only use the representation for loves and mama. So in this attention matrix, what can we do? How can we adjust this attention matrix to enforce the requirement that was suggested? We're going to transform this attention matrix using causal masking. How do we do that? We're going to do the simplest possible thing. What's the simplest possible way to do what you're suggesting? Yeah. Exactly. We zero out everything that occurs above the diagonal. Anything that occurs above the diagonal, that involves a word looking at a future word. We can't allow that. So we zero them out. There's only one problem here with what we've done. One slight problem, which is what? I've zeroed out everything above the diagonal. Am I done? Remember, these are attention distributions. Each row needs to be a valid probability distribution. We need to make sure each row sums up to 1. And the way that we do that is just by taking the sum of each row of each new row and dividing each element by that sum. So I'll call these new things like A twins. So they're proportional to the old attentions, just reweighted so that each row sums up to 1. Okay, that's it. That's how we solve this time travel problem for transformers. We've now defined, we have a perfectly valid way of predicting the future from the past where we can't cheat and look at the future in order to solve the problem. Any questions? Okay. So there is one remaining problem that we mentioned last time. What was it? So we solved this causal masking issue, but there was one issue that we have not addressed yet. Yeah. The word order issue. The word order issue. So there's no real way for the model to know what position each word occurs in. We have word vectors here. So we have the first word vector, the second word vector, and so on. But these are, if the word llama occurs in the first word, that's the same vector as if it occurs in the 10th word. Right? It's based on the vocabulary. It doesn't, the vector that you get doesn't depend at all on where you are in the sentence. So llama has the same vector, the same input vector, no matter where it occurs. So from the perspective of the model, if the model doesn't know which word is in which location, we need to solve that problem. You cannot just permute the positions of words and expect to get the same results. Your model has a problem with it if it thinks it can do that. So what can we do? What's the dumbest possible thing that we can do? Yeah.
I guess it's like have a constant weight for each one of the A's. Like first one you weight is 1.5 and 1.4 is 1.
So it's not going to be in the attention because we want the attention to be learned. So we want the model to be able to learn where to attend to. So we don't want that. I think we don't want it to screw up the model's ability to learn to do attention. Yeah. That's exactly it. So those are called positional embeddings. Each possible position, 1 through n, gets a vector. And we'll call it pi. So we have a distinct vector for each possible location. And so remember, like all of these models that we're dealing with, every transformer model has a maximum context length, right? For older language models, it was like 512 or 1024. For standard GPT now, it's 4,000 or 8,000, and then there are these super long models that have versions of the model that have 128,000. No matter what it is, though, there's a fixed maximum input length that these models can have. So we just list out what are all those possible positions. You can be, if your maximum context length is 1024, then you have 1024 possible positions that a word could go in. You have a separate vector for each of those positions. And then your new word representation, your new input representation, I should say, is pi plus wi. So for the word llama, up here, it's the first word that occurs. So you take the word embedding for llama, you take the first positional embedding, because it's in the first location in the sequence. You add them together. That's it. Now, where do these positional embeddings come from? What's the simple possible answer? You learn it. And it works pretty well. So everything in the model, your word embeddings, your weight matrices, your positional embeddings, they're learned through backpropagation. You have your loss function, which says, I want to predict the next word given the previous words. You minimize your loss by adjusting all of these weights at the same time. Now, I'll mention, there are a number of different positional embedding techniques in the literature. So learned positional embeddings, they're probably not the best thing. There are some slightly fancier things that people do. So there are things called rotary embeddings, there's something called alibi. There are probably ways to improve it, especially for very long sequences. If you start from positional embeddings, though, you will get a pretty strong baseline. They're not quite state of the art, but they work very well. Certainly well enough for any beginning language model to do. Okay, that's it. Yes. I mean, so the information's been smushed together. Is that what you're saying? It's not necessarily you're not necessarily going to be able to uniquely recover both. Is that the concern? So the model will learn to, these are extremely high dimensional vectors. There's not going to be a way to linearly decode, but there is going to be a way to non-linearly decode both of those pieces of information in general. So I'm trying to think if there's a clean geometric way to illustrate this. Let me give so very, very simplified example of what something like this will look like. Imagine that our position and word embeddings are both two-dimensional. Okay, so we have llama, our word embedding for llama over here, and we have only two words in our vocabulary. We have mama over here. We have P1 over here. That is the first positional embedding over here, and we have P2 over here. Now we can sum together llama and P1. We can sum together llama and P2. Those will be distinct vectors, and they'll also be distinct from mama plus P2 and mama plus P1. So the four possible combinations will be here. We're not adding another dimension necessarily. Here we are. I mean, it didn't have to be necessarily adding another dimension. It could be that we have actually we could have had 10 words, each sort of evenly spaced, as long as the positional embeddings are distinct. Basically, what we need to make sure is that the mapping is one-to-one. I believe that will. I'm fairly sure that's achievable in almost every situation to have a one-to-one mapping here. And as I mentioned, it doesn't necessarily mean that things will be linearly decodable. So if you just do matrix multiplication, you may not be able to figure out which of these you're in, which combination you're dealing with. But if you have the ability to do nonlinear decoding, which neural networks do, right? They do matrix multiplication followed by nonlinearities. Then you'll be able to figure out which combination you're dealing with. And so everything's going to be learned. Exactly how to position all these words in this space, and then how to interpret which words you're dealing with. Any other questions? No. Okay. So let me talk now about a very important engineering detail, some very important engineering details in all of this, which is it's very, very closely related to why transformers took over the world. Have we talked about the bitter lesson? No, I haven't sent out this essay. I'll have to send out the essay to everyone. It's every year this essay becomes more and more true. When I read it, it came out in 2018 or something, 2019, and I first read it and I thought this is outrageous, this is insulting, and my opinion about it has been updated every year since then. So what does the bitter lesson say? It says intelligence comes from lots of computation. If you increase the primary way that you're going to increase the intelligence of systems is by increasing the amount of computation in those systems. The reason why transformers have been so effective and why people switch to them almost immediately, why they really, really work, is that you can process sequences really quickly with a transformer as compared to an RNN, a recurrent neural network. Let's talk about why that's true at a high level, and then we're going to go into some low-level details about why that's true. Let's look at the RNN architecture. So remember, you did this on your homework, so hopefully this is very familiar to all of you. So if you want to process a sequence of n words, what do you have to do? What are these boxes telling us that we need to do? Yeah. Exactly, everything's sequential. So in RNN, we process all the words sequentially, one word after another. In a transformer, we don't have to wait until the first word is done processing to process the second. We're processing everything in parallel. The consequence of that is we're able to, in a fixed amount of time, we're able to process many, many more words with a transformer. What that means is we can do more computations in the same amount of time, and we can process much, much more data in the same amount of time. So in the time that it took an RNN to process 1 million words, we may be able to process 1 billion words with a transformer. I know maybe it's off by it might be a factor of 100 difference. It's a very large difference nonetheless. So let's see why that's true, and let's look at the matrix formulation of the transformer. So we have our sequence of words. We'll start from the very top, the very bottom, I should say. We have our sequence of words, W1 through WN. What we're going to do is we're going to put this sequence of words into a matrix. Let's call it just capital W. So we have a new matrix of words with n columns in it, 1 column per word. Where have we seen this before? We did this one time previously in the course. Where have we seen it? Yeah. Not quite. The embedding matrices, so because the embedding matrices are for everything in the vocabulary. So when we were talking about MLPs, right, we were talking about how you could process a whole sequence like as a how you can think about MLPs as just a big matrix computation. That's what we saw something similar there. Okay. Now, let's look at attention. Can someone remind me what are the steps involved in attention? So we have our attention matrices, right? We have the attention distributions. How do we compute those attention distributions? There were a few high-level steps involved. There were some dot products, right? What were we do? What did we do first? Yeah. Okay, great. So what we're going to do first is do a query and key transformation on everything, right? So we have a query matrix Q, query weights Q, key weights K. So we'll then we're then going to create a new matrix. We'll call it WQ. So this is the words transformed into their query vectors. So how do we do that? What we're going to do is take the Q matrix times W. And what happens now? In the first column of this new matrix, we have the query vector for word 1. In the second column, we have the query vector for word 2. So each column contains a query vector. We're going to do exactly the same thing for K. We're going to multiply the K matrix by W, our word embeddings, and that gives us a key vector in each column. So rather than, the way we were presenting it before, what's the point of doing it this way? The way that we were presenting it before is that we were sequentially going through each word vector and multiplying it by the key matrix and the Q matrix, the query matrix. So it was very sequential the way that we were talking about. It doesn't need to be sequential. All we're doing here is we're parallelizing. We're putting everything into a matrix, doing all the computations at once. Why do we want to do that? Is because GPUs, graphical processing units, they do matrix multiplication really, really quick. So our attention matrix. How do we compute this? How do we compute this in terms of these two new matrices that we have here? It's going to be a matrix multiplication. It's going to be a softmax and a matrix multiplication. So what do we do? So remember, the queries are looking for keys. So each word has a query, and it's taking a dot product with all the keys to see which key should it look at. And that gives us a weight. So we're looking at similarity between queries and keys, giving us a weight, a distribution of weights for each query. What I'd like is for the queries to be on the rows. Yeah. So we're going to take the transpose. So taking the transpose flips the query, one query per row now, and we multiply this by WK. So we'll do this in 2 steps. So we'll call this like this. So these are the scores, we'll call them, like attention scores. They're not attention probability yet, because it's not actually probability distribution. They haven't been normalized. Then we're through softmax. So what does this give us? Let's actually look at what this matrix involves. So we took the transpose. So now it's one query per row, and we still have one key per column. So what this looks like is that we have Q1.K1, Q1.K2, Q1.Kn. And then on the second row, it's Q2.K1, Q2.K2. So now, same one query per row, taking dot product of all the keys. So each row now represents sort of the weight that each word assigns to every other word. Each query assigns to all the keys. And then our attention matrix, the actual attention distribution. So let's call this thing S. This is equal to softmax of S, where the dimension that we're doing the softmax along is equal to 1. So we're doing it along the rows. Is that right? I'll indicate it like this. We're taking the softmax of each row. So we have n different softmaxes, 1 for each row. So what's the consequence of this? Which is we can compute the full attention distribution. We got the queries and the keys by matrix multiplication. We got the attention scores by matrix multiplication, and then we got the actual probability distributions by taking the softmax test. So almost everything that we've done, almost all the computations are just matrix multiplications. Matrix multiplications are fast, and we process all the words completely in parallel. We also have to apply causal masking here. I've left that out. That's also a very simple operation. It just involves multiplying 2 matrices, actually. You have a causal mask that says everything above the diagonal should be 0, and you multiply by that matrix. Okay, so what's left to do for attention at this point? We'll multiply. You're right. So we have to sum together all the values. Right? We have to take a weighted sum of all the values. So what we need is a value matrix. So we have our value weights V, and then what we'll say is that WV it's going to be a matrix that collects up all the values for all the words. It's going to be V times W. And so what we have there is one value, so the first value in the first column, the second value in the second column, and so on. So I have my attention matrix. I have my value matrix. I have the values for each word. How do I combine those two things in order to get the new word representations? So I have I get my updated word representations. How do I do it? It's going to be my weighted sum of the value vectors. So we have here rows, that's right. So how do I actually do this? So it's going to be, you're right, we have our attention matrix here, where each row is normalized, right? One row corresponds to the distribution, the probability distribution over attention. So first row is what does the first word attend to? So it's going to be A times what? Is it times WV? The dimensions here actually tell us what it has to be. So A is an n by n matrix, where n is the sequence length, right? What are the dimensions of this matrix? The value matrix. So okay, I think I said this when we were doing the MLP computations earlier in the quarter. I think I said I'm acknowledging this is not the most exciting thing ever. Okay, I can see from looks up people's faces. No, it's not thrilling, and it should seem remarkably similar to what we did there because it is. However, this is the actual reason why deep learning works. If you do not have this, you don't have deep learning. We have all these cool ideas about attention, blah 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 blah. Human mind, blah 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 blah. None of it matters if you cannot transform your problem into a matrix multiplication problem and do it really quickly. None of it matters. It also works. Like this is why this works. So that's why we're talking about this. And the fact that it's very boring means that most people don't pay attention to it, and therefore most people aren't going to be making money by actually understanding what works here, right? The stuff that's boring but important is exactly where you should be focusing your attention if you want to make an impact. So, what are the dimensions of this matrix here? Yeah. Right. Okay. So what's the dimension of the value matrix? So it's n here, n being sequence length. Yeah. D being the embedding dimension. Right. So this is n by d. A is what? It's n by n, sequence length by sequence length, because we have words attending to each other. So what's the only thing that can work here for doing matrix multiplication? Transpose. So it's going to be WV transpose. And what we get out here is a little ugly right out. So what we get out here is on every row, we have our new word representations hi. So what's hi? So we have a vector hi on the ith row. That is the vector corresponding to the updated representation of word I, which is what? It is a weighted sum from j equals 1 up to n, aij times vj. So what are we saying here? aij, that's the attention that word I pays to word j. So we're summing over the j's. Everything that word I pays attention to, we're summing over that, and we're multiplying by the value vector for word j. So we're taking a weighted sum over all of the value vectors, and we're putting each of those new representations on the ith row. So that's it. We're done with attention. Right? Every single attention layer can now be broken down into just a bunch of matrix multiplications and one little softmax in the middle. Yes. Right here. Right. So you can do it here or here. It's basically the same thing. People actually do it at this stage. Basically, it's when you get your attention distribution and you mask it. So we will say do causal masking here. Okay, so we've taken care of attention. Attention is just a bunch of matrix multiplications. What about the MLP? So it's actually a little different from the MLP that we did before, so let's talk about it. Let's start from here. How do we parallelize the MLP? We've already parallelized an MLP once. It was different. So what was different about the MLP that we did before is that it did not process each of the words independently. In this case, the MLP processes the words completely in parallel. So what was our definition of the MLP? It was that you take in a word representation. We'll call it MLP of x. Okay, you take in let's call it xi for the ith word vector. So what happened? You have a weight matrix Okay, so you took in the ith word vector, xi. You multiply it by this weight matrix, WMLP, 1. You do a ReLU. You multiply that by another weight matrix. You do that for every single word. So we can frame this in a completely sequential way. You do this for the first word. You do this for the second word. You do this for the third word. Now, we don't want to do that. We want to do this all in parallel. So let's talk about this in terms of just my word matrix up here. So I'll change these x's to w's. You're not directly processing the word vectors. You're processing. Well, actually, let's do this in terms of the h's. Just it's just what name we give these vectors. That's all that we're talking about here. But we'll do this in terms of the h's. So the h's, where I mean here. So let's call this thing h. So we have this matrix of our updated word embeddings from attention, right? One per row. So how do I apply the MLP to that entire H matrix, all of the word embeddings in parallel? So okay, I have H is equal to H1, the representation for the first word, H2, the representation for the second word, and so on. One per row. So I want to parallelize this. Well, it's a good idea if you're talking about independent sequences. But here I'm talking about a single sequence. So each is the H. I'm taking the H notation from what I did over here, where I have my updated word representation. So one H, HI represents the updated word representation from attention for word I. So each of the HIs, they're all in the same sequence, right? So I have one sequence with 1,000 words in it. Right? I have 1,000 words. So I have n equal 1,000. I have 1,000 H's as a result. But they're all from the same text. If they're all from the same text, I have to run them through the transformer at the same time. I can't do backpropagation independently on them. Otherwise, I would be processing each word in a text completely independently. That's like having a transformer with context length equal to 1. The words influence each other's meaning, so I need to take that into account. So how do I turn? Maybe I didn't state the problem clearly. Do people understand what I'm asking for? What I want to know is, like, I've given you an algorithm for applying an MLP to a single vector H. How do I parallelize? How do I turn that single vector computation into something that happens simultaneously for all the vectors, into a matrix multiplication? Yeah. H transpose. That's it. So. So the thing I do here is I multiply WMLP times H transpose. And right, because I have now, that gives me out in one column, I have the result of MLP applied to H1, the first word vector. In the second column, I have MLP applied to H2. So each column now contains the MLP applied to each vector. So that's how we parallelize. It's literally just like instead of inserting a vector into this MLP equation, we insert a matrix into the equation. Nothing really changes. It just means we've done more computations at the same time. And that's it, right? That's like what happens in the transformer. There's a tension, there's an MLP, and there were two other things that happened. There was a residual connection, which is an addition. Residual connection just means you add what you did previously to what you did now. And then we also had the layer norm. So the layer norm actually turns out to be like not very parallelizable. So, but it's also very, very few computations relative to this. Very few floating point operations. So it doesn't really matter. I mean, it only matters, like, there are people who care about fast layer norm representations running on a GPU, but you're talking about a couple of percentage points of, how much time it takes to run this thing. So it's not a big deal. Not a big deal for you. Like, it's a big deal if you're like, look, OpenAI is spending like billions of dollars per year, running their GPUs right now. So they actually do care about those percentage point savings. That, like, 1 percentage point to $10 billion is $100 million, right? That's a lot of money. So you people care about that a lot. But for the purpose of this class, it's not that big of a deal. Yeah. Can you what? Yeah, of course. No. Oh, no, I didn't. Maybe the message might have been there, but I was too locked into what I was doing, I guess, to notice. Oh, it has a little birthday hat. Maybe I saw it. I didn't even notice. Happy birthday. Yeah.
Does the border pass can be parallelized this way in backpropagation?
Fantastic question. Yes, everything in the backward pass can be parallelized as well. It's just another matrix multiplication. In fact, I believe in your homework you implemented the parallelized version of the backward pass, or at least I encourage you to. So for the NLP, right? In problem set 3, there was a parallelized version of the backward pass. Yeah, it looks very, very, very similar. Great question. Yes. The results won't be quite as good. I mean, so for one thing, the NLP will be. Let me not even try to give a justification for why that's true. People, I mean, basically every little iteration of this, people have tried, and this one works the best. It doesn't mean it's the best architecture. Just among like little tweaks that you can make, this is the best one that there is. I mean, it's a good question. It just happens not to work as well. Any other questions? talk about one more thing. What I want to ask now is how many floating point operations, by which I mean, by floating point operation, I mean like a multiplication of two numbers or an addition of two numbers. I don't mean matrices, I mean numbers, okay? How many floating point operations, so additions and multiplies, happen in attention and the MLP? So let's do attention first. And you assume that it's like you're using like a very, very straightforward algorithm for doing matrix multiplication. Okay, so what I mean is just the algorithm you learned in high school, where you take each column and you multiply it by the rows. And, okay, so we have what were the computations that we did for attention? We have I erased the important one over there. So let's write it down over here. We can ignore the softmax as well. But we have WV is equal to V times W, and then we have H is equal to what? It was A times WV transpose second. Okay, so we actually, this is everything that happens for attention. We have everything that happens for MLP up there. So we have 1, 2, 3, 4, 5 matrix multiplications that happen for doing attention. Let's count up how many floating point operations happen in each of them. So how many floating point operations happen here? So how many floating point operations? So when we multiply two matrices together, when it's happening, so we have like x1, x2, x3, x4 times y1, y2, y3, y4. Where we get out x1, y1 plus x2, y2, x3, y1 plus x4, y2, x1, y2 plus x2, y4, x3, y2 plus x4, y4. So the way that I would count this up is I would basically say that we have 1, 2, 3, 4, 5, 6, 7, 8 multiplications, and then we can count this as basically let's say that this is two floating point operations for the addition. Let's count it like that. So I have 8 plus 8, correct? So I have 16 floating point operations. So what's the general formula there? Right, we're out of time. I may not decide to continue this next time since it's going to require a lot of setup. Let me give you a punchline. You can confirm this for yourself.